here. Okay, I'm recording right now. So, Seattle, thank you very much for accepting our invitation. Welcome to this talk series from the AML-CS group in Universidad del Norte, Colombia. So we are very glad to have you here, top research from Norse, from Norway, basically.
Thank you very much.
Yeah. And thank you again for accepting our invitation, and we are ready to hear your talk. Thank you. So okay, let me make you co-host so you can share your screen. Yeah, you're ready.
That's great. Yes. Let me see. Yeah. So I have shared my screen, and can you see it now?
Yes, we can see.
Okay. Very good. And then let me yes. So then, so first of all, I would like to thank Ania's invitation, and then I'm very much honored to give this presentation to your group. And then so today I'm going to talk about some of our recent technical developments in our data assimilation workflow applied to some subsurface characterization problems. So here is the outline of the talk. I will basically give a brief background regarding the subsurface characterization problem. And then, of course, we are going to apply our ensemble-based data assimilation workflow to tackle this problem. And then I will list some of the challenges that we found actually during our applications to this problem. And then after that, I will present the details of our technical developments that are used to tackle these noticed challenges. And now I finish this talk with some discussion and conclusion. So here on the left-hand side, you will see a figure. So this is basically you will see actually a survey sheet here. It shows some seismic wave into the subsurface model. And then because of the heterogeneity in the subsurface, some of these waves will be reflected and then recorded by some sensors that are put on the sea surface. So this is typical, actually, inverse problem that we might encounter in the subsurface characterization problems. So in such a problem, our purpose is to use the observed field data sets, like for example, this recorded seismic wave to invert for some properties of the geological formations. And of course, I mean, in this particular example, the purpose here is to use this seismic data set to find possible places of hydrocarbon, right? Because this is a valuable asset in the subsurface. And then in a subsurface characterization problem, the typical types of field data include, for instance, production data from field well, seismic data, electromagnetic data, gravity data, fiber optic data, and so on and so forth. So then we can have a look at these subsurface characterization problem from a more mathematical point of view. So in this problem, what we have includes the observed field data sets. And then often we will have some initial guess of the subsurface model. I mean, if we follow the concept data assimilation, normally called this background model or ensemble of background models. And then, of course, we will have typically nonlinear forward simulator, denoted by G here. So then this simulator will map input subsurface model into the observation space to obtain some simulated field data sets. And then in this characterization problem, our objective is trying to find one or multiple sets of subsurface model in such a way that their corresponding simulated data can match the observed field data to a good extent. So that's the whole purpose here. And then formally we can tackle the subsurface characterization problem by solving the following regularized minimum average cost problem. So I call it the MAC problem in short. So in this MAC problem, our objective is to find an ensemble of updated subsurface model so that it can help to reduce the average value of an ensemble of objective functions or cost functions. And then in each of the cost function, it contains two terms. So the first term is the data mismatch term. So basically, it describes the distance between the observed and the simulated field data sets. And the second term is a regularization term. And normally we introduce a regularization term to promote certain, for instance, desired properties in our estimated subsurface model. And then if we let this regularization term to be this, let's say, weighted projective function, then we can see that basically this cost function is in the form of a nonlinear least squares. And then we can show that the previous MAC problem can be approximately solved by the iterative ensemble smoother. And this model update formula is given in this form. So if you are, you are actually familiar with the Yankev, different types of Yankev algorithm, and you will actually clearly see there are some similarities between the model update formula presented here and the Yankev update formula. And then we actually, in our practice, we like the iterative ensemble smoother. So I use IES for short a lot because it carries a number of practical benefits. So one of the benefits is that it's a non-intrusive, like many other ensemble-based data simulation algorithms. So by non-intrusive, it means that we don't have to actually know the, for example, the source code of the forward simulator in order to calculate the gradient of the objective function with respect to the model variables. And yeah, and then it's also derivative free. So by saying that, we mean that we don't have to explicitly calculate the gradient of the objective function with respect to model variables, but implicitly it does. We do use the gradient information. And is also able to provide uncertainty quantification to some extent. Of course, we all know that, I mean, like the conventional ensemble-based method is very difficult to actually very correctly quantify the uncertainties in our estimated results for various reasons. So often we'll see that some underestimation of the uncertainties. So this is a common problem. And then the last point is that the IES algorithm is able to handle very large subsurface models. So that's why, I mean, in our field, people like to use it because of these noticed practical benefits. And then here I listed some challenges that we found during our applications of the iterative ensemble smoother to subsurface categorization problems. And I guess maybe some of the problems you might also encounter in your applications of ensemble data simulation methods to your own problem. So one of the challenge is about the big data. So for example, if we are going to use the 4D seismic data, then we are going to get a very huge volume of the data set. And then direct consequence of these huge volume is that we are required to put immense computational resources in order to handle such a big data set. And another challenge is actually related to the adverse effect of a small ensemble size. in our problems, normally we use ensemble size around 100. I mean, this size seems, as far as I know, seems to be kind of a bigger, maybe to the size that you often use. But even though we use is a higher number, still we see that the adverse effect of a small ensemble size, for instance, like sampling errors and no rank issues, are already substantial in our problems. And then with this adverse effect, normally we will form the downgraded data assimilation performance if we do not do anything to tackle this issue. The third problem is related to model errors. An example is that, as I mentioned before, normally if we do this characterization problem, we will have a numerical forward simulator. And for various reasons, this numerical simulator is imperfect. And then, of course, this imperfection will cause problems in our data assimilation problem. And then the last issue is related to the physical constraints. I'm not sure if it is correct, but in my impression, it seems that many data ensemble-based data assimilation algorithms, it seems it's not so flexible, actually, to take into account physical constraints. Please correct me. I mean, if you do come across any work that actually present a very nice work to handle genetical constraints in data assimilation problems. And then, and yes, so I'm not sure how much time I might spend on all these talks. So if I don't have enough time, I might skip some of the.
You're good. You're doing well. You're doing well in time. So
okay, yeah, just no problem to remind me if I'm going to run out of time. Okay, then I will skip some of the content.
It's like being home. Okay. Feel it that way.
Okay. Yeah, okay. Thanks for that.
Okay.
Okay. Then I will move to our technical developments and that are developed to handle these as these four noticed challenges. So then the first topic I'm going to present here is about big data assimilation. And the main objective is to tackle the issue of big data. So that's the first issue actually I mentioned in our identified challenges. And then to tackle big data assimilation problem, our main idea is to use the concept of sparse data representation. It's also known as dimensionality reduction in the jargon of machine learning community. Okay. Then, so first here I present a conventional workflow. If we don't take into account the dimension issue. So in this workflow, let's say we have one ensemble of a subsurface model, and we just put these subsurface models into a forward simulator to get the simulated data. And then we compare the differences between the simulated and observed data, and then use a data simulation algorithm, here is IAS, to update the subsurface models in such a way that after update, the simulated data can match the observed data better. But to tackle the issue of a big data, then we introduce an extra procedure called a sparse data representation. So the basic idea is that before doing any update, we apply a certain transform to both the simulated and observed data. And then after transform, these both sets of data will be represented by some representation coefficients in the transform domain. And then we actually only select a small part of the representation coefficients, which is called the leading representation coefficients. And then we use these leading representation coefficients from both the simulated and observed data as the real observations and the simulated observations, and then feed these two into the data assimilation algorithm to update the subsurface model. So here I'm going to give an example. So that was done in one of our recent work. So in this example, we use discrete wavelet transform to handle big data. So here is the basic procedure. So suppose that we have one or multiple sets of seismic data, which can be either 2D, 3D, or actually 4D. It's not a problem. Then we first apply discrete wavelet transform to the seismic data to get a set of wavelet coefficients. Now, these wavelet coefficients are the representation of the original data set, but it's in the wavelet domain, right? Then we have a procedure that allows us to estimate the noise levels in each wavelet coefficients. Then based on the estimated noise level, we can calculate the threshold value. Then we compare the magnitudes of the wavelet coefficients to the threshold value. So if the magnitude of our wavelet coefficients is above the threshold value, then we will just keep that wavelet coefficients as it is. On the other hand, if the magnitude is below threshold value, then we'll just set that wavelet coefficient to 0. So that will modify the value of that particular wavelet coefficients. And then by doing the thresholding, we will end up with a set of leading wavelet coefficients. And then they will be used as the effective observations in ensemble data assimilation later. In doing so, I will show that we can actually very efficiently reduce the data size. And then we can construct the observation error coordinates matrix in the wavelet domain as a byproduct of our procedure to estimate the noise level. And then this procedure is generic, and it can be applied to different types of geophysical data or image like geophysical data, like seismic data, electromagnetic data, and maybe satellite data, which I didn't try. But I know that the people are also applying this sparse data representation to handle EM data. And then I'm going to use a 2D example to illustrate the performance of the wavelet-based sparse data representation procedure. So here we have a 2D reference amplitude versus angle data set. So this is one type of the seismic data. And then we add some artificial noise, actually it's a white noise, onto this reference AVA data. After that, we apply a discrete wavelet transform to the noisy data to get a set of wavelet coefficients. So as I mentioned before, now this set of wavelet coefficients are the representation of the original noisy AVA data. Then we apply the thresholding procedure to these wavelet coefficients to obtain a set of leading wavelet coefficients. So then if we apply an inverse wavelet transform to this set of leading wavelet coefficients, we can actually get reconstruct, let's say, an AVA data set. So if we compare the original reference AVA data set, which, I mean, this reference AVA data does not contain any noise, and then this is a reconstructed data based on the noise AVA data. So if we compare this constructed data and the reference data, we can see that the reconstructed data bears a very similar structure to the reference data, right? And then if we compare this one to the original noisy data and it appears less noise, it means that we actually remove some of the noise in the original noisy data set, okay? So this means that this sparse data representation procedure can actually help retain useful features contained in the original data set while suppressing the noisy components. So it is actually something quite good. And then what I want to stress is that, I mean, during the data assimilation process, it is the leading wavelet coefficients that are used in ensemble data assimilation. And in this particular case study, the number of leading wavelet coefficients is only about 6% of the original noisy data or the reference data. And then the true noise level is actually this number. And then through this noise estimation procedure, we get the estimated noise level, which is given by this number. So if you compare these two numbers, they're actually quite close. Yes. And I also noticed that, I mean, there are some other types of sparse data representation procedure that people have used. So for instance, one can use machine learning to do sparse data representation, or maybe use some machine learning model like the convolutional neural network to do sparse data representation. So as I mentioned before, actually, we can adopt lots of machine learning models for the purpose of dimensionality reduction, right? If we are familiar with this kind of tools. But of course, I mean, sparse data representation procedure is not the only idea that can be employed to handle the problems of big data. And then an alternative is to adopt the concept of a local analysis. This is exactly, I think, like the idea of local ETKF that I guess you guys have been working on it a lot. Okay, and then I'm going to move to the next topic. So it's about the correlation-based adaptive localization. And our objective here is to tackle the actually the adverse effect caused by a small ensemble size used in ensemble data simulation. But then we do have a special challenge here. That is, if you recall the sparse data representation procedure that I mentioned previously, if we do that, then the original data is represented in another domain, and then it is the representation coefficients that are used as the data. So by doing so, the representation coefficients normally will not have a clear definition of physical locations, right? So if we want to apply the conventional, like physical distance-based localization scheme, which requires that both the model variables and the observation data have physical locations in order to compute the physical distance, either between model variables and model variables, or between model variables and observation data. But here, if we do sparse data representation procedure, then the effective data doesn't have a physical location. So for this reason, we actually cannot apply the conventional physical distance-based localization to tackle the issue of small ensemble size. So then we actually developed something called the correlation-based localization. And then in this, before I move forward, let's briefly have a look what localization means in our workflow. So here I present the model update formula in the IES. When no localization is conducted, and here this term represents the common game, right? So right now there's no localization. But if we want to do localization, we normally do something called the common game type localization. So we replace the original common game matrix by a sure product of the common game matrix and the localization matrix. And of course, normally we will say the elements of the localization matrix has to take a value between 0 and 1. Now the main issue is that how should we construct the localization matrix? So in our work, the main idea is that we use the concept of causal relation detection to design the to actually construct a localization matrix. The main idea is like that. So suppose that we have a particular model variable and a particular data point. So then first thing is that we are going to ask, is there any causal relation between the model variable and the data point? If so, then that's okay. Since the model has caused the data, or it means actually the model variable has an influence on the data. Then when we do data simulation, we actually should use this particular data point to update that particular model variable. On the other hand, if we cannot find a causal relationship between the model variable and that particular data point, then I think it's better to actually exclude that particular data point. We just don't use this data point to update this particular model variable, or at least we should reduce the inference of this particular data point on the update of that particular model variable. So this is the main idea here. Okay. Now, based on this notion, then we actually need to detect the causal relation between the model variable and the data. We adopt the sample correlations because it's quite easy to compute. It's not very complicated. And then we will just say, okay, the elements of the localization matrix should be a function of the sample correlation between the model variable and the data. Then in our implementation, we tried two types of function f. So one choice is the Heaviside step function. So if we are going to use this one, in effect, is equivalent to saying that we introduce a threshold value, and then we compare the magnitude of our sample correlation to that threshold value. If the magnitude of the sample correlation is above the threshold value, then we say, okay, then there's a strong evidence that there's a causal relation between the model variable and the data. Then we say, okay, the localization coefficient or the tapering coefficient will be set to 1. If the magnitude of the sample correlation is below that threshold value, then we'll say, okay, maybe there's no causal relation. Then we'll say, okay, then we should exclude that data for model update. Then we'll say the tapering coefficient should be set to 0. So one issue related to this Heaviside step function is that it's not a continuous function. So sometimes we notice that it might cause some artificial effect, like discontinuities in the updated subsurface models. So for this purpose, we adopt the Gasparin-Cohen function actually to compute the localization coefficient. I'm going to skip the details how we compute this one. So if you are interested, you can have a look at the second paper I listed here. It's an open access paper, so I think you will be able to find it online for free. Okay. By the way, I also want to mention that as far as I know, a few other researchers are investigating other types of tapering functions that can be used to compute the localization coefficient based on the sample correlations. So maybe hopefully in the future we will see some of these reports published. So here I'm going to use two examples to illustrate the performance of this correlation-based adaptive localization scheme. So in the first example, actually we use the say the wavelet coefficients of a seismic data set as the data. So for this reason, as I explained before, we cannot apply the physical distance-based localization scheme. So that's why instead we have to use the correlation-based localization. And then we compare the results when we don't do any localization and the results when we do correlation-based localization. So on the left-hand side, I present the results. So here actually the results is about the box plots of some root-mean square errors at different iteration steps. And then when we do not do localization in the IES algorithm, then as the iteration goes on, we can see that the spread of the box plot becomes smaller and smaller. So this is a strong sign indicating that maybe the phenomenon of ensemble collapse actually happened. On the other hand, if we apply correlation-based localization to the IES algorithm, then immediately the phenomenon of ensemble collapse is gone. We can actually maintain a substantial spread in the box plots at all iteration steps. Okay. And then in the second example, yeah, it's a similar case study. Where we used wave coefficients as the observations. But then the second example actually reflects another problem if we do not do localization. So in this particular case, again, on the left-hand side, these are the results when no localization is done. So in this case, there's no actually ensemble collapse happening when we don't use localization. But we have another problem, that is, if you check the value of this mean square errors. So at the first few iteration steps, we can clearly see the decrement of the mean square error, right? However, afterwards, then the mean square error start to rise. This is because if we do not do localization, then we are not actually, in a way, suppressing the spurious correlations in our update formula. Then the IES algorithm tends to overfit actually in the observations. So then the overfitting actually leads to worse results in comparison the case that there's no overfitting. On the other hand, if we apply the correlation-based localization to the IES algorithm, then we get a very nice results. So the mean square error always tends to decrease as the iteration process goes on. It means that it's better to do more iterations, and then we are not to get worse results if we put more computational resources on the computation. As least we do not waste our computation resources to find the worse results than not doing so. Okay. Then in one of our another recent paper, we discussed the practical benefits of the correlation-based adaptive localization over the conventional physical distance-based localization. So here I list some of the benefits that we found. So first of all, of course, is that if we use correlation-based localization, then it's independent on the availability of physical locations of either model variables or the observations. And then interestingly, we can also show that the correlation-based localization can also very nicely handle non-local observations, which is actually a long-standing challenge for the physical distance-based localization schemes. And then the correlation-based localization scheme can also take into account the time-lapse effect of observations. So what is a time-lapse effect? So if you imagine that if you are doing a data simulation problem, likely you might collect observations from same physical location, but at different times. Normally, for a physical distance-based localization scheme, then you will have used the same, localization coefficient for observations from the same physical location, right? However, in reality, actually, because the dynamics of the system could change over time, then I think it is actually more sensible to also adapt the localization coefficient with time. And then it can be shown that the correlation-based localization can take into account this time-lapse effect. And they also can be adaptive to different types of model to data pairs. Because actually we are computing the correlations between model and the data, right? Then for different types of model and data, maybe the correlations are different. And then so in this sense, we'll be able to adapt to different combinations of model variables and data points. And it's also adaptive to the ensemble size because if you recall that I mentioned the threshold value, if we are going to use the step size, the Heaviside step function, because that threshold value is in a way depends on the ensemble size. So then in effect, this correlation-based adaptive localization also depends on the ensemble size. We are actually adaptive to the ensemble size. And then one additional benefit is that actually the flexibility in practice. You know, if you are going to use physical distance-based localization, And sometimes people have to separate the localization scheme for the vertical direction and the horizontal direction. I mean, I'm not sure if you come across this problem. However, if we use correlation-based localization, then basically there's no difference. We can use the same localization scheme for different types of models, whether it's a 2D, 3D, it's actually no difference. So this means that you can just implement the same localization scheme and it can be easily extended to different case studies. So there's really one practical advantages. Because in our problem, like for example, if we consider a reservoir model or subsurface model contains many field wells, and then if we're going to use say distance-based localization, then the data or the observation are from the wells. This means that for each well, you have to choose a land scale to construct the tapering or the localization matrix. It's actually very labor intensive, but for the correlation-based localization, you don't have to do that. So it's very convenient to implement. And then so here is a little bit self-exaggeration of the use. I just found that recently there's some industry or academia use of our correlation-based adaptive localization scheme. So for instance, in one of these US GS software, I think it's implemented this correlation-based adaptive localization scheme, and also commercial software for reservoir engineering. It's actually for this oil and gas industry. Also implement that because they use an ensemble data simulation workflow to tackle this subsurface characterization problem. And then I'm not sure whether I should say that, but we have a planned implementation of this correlation-based adaptive localization scheme in the software platform of a major energy company in Norway. Yes. So then the next topic is about the combination of data simulation and machine learning technologies. So I think it's a really hot topic these days. Our main objective here is to tackle the presence of model errors in the subsurface characterization problem. And then to handle this problem, our main idea is to describe the model errors through a parametric machine learning model. And then let's explain the situation first in order for us to better see why we should use machine learning to handle this problem. So, let's first consider how we get these observations. And normally we correct the field data sets as the observations, right? But we might say, okay, this field data set might be generated by some underlying true subsurface model, which is unknown to us. And then there's also an unknown forward simulator that map this true subsurface model to the observation space. In reality, however, we normally use a numerical simulator denoted by J here to map an input subsurface model into the observation space to get the simulated data. And then due to various reasons, this numerical forward simulator is typically imperfect. This means that this function H and then this numerical simulator G will not be equal to each other. Now, of course, this imperfection in the forward simulator will definitely affect the performance of our data simulation algorithm. Then how should we handle this problem? So first of all, let's consider this. We can actually decompose the observations into two terms. So the first term comes from this imperfect forward simulator, right? It's basically generate some simulated data in order to match the real observations. And then the second term describes the difference between the observed data and the simulated data. And then we call it a residue functional. In practice, actually, the challenge is that we do not know the exact form of this residue functional. So what we can do? Then to tackle this problem, our main idea is to approximate the residue functional by a parametric machine learning model, so that after approximation, this residue functional will depends on both the input subsurface model and the parameters associated with the machine learning model. And in one of our recent work, we implemented a kernel-based machine learning model. So I'm going to skip the math details here. But of course, other types of machine learning model, like the channel deep neural networks supported by machines, can also be used, as long as they can serve the purpose of functional approximation well. And then with this approximated residue functional, then we can actually tackle the data estimation problem in a new MAC problem. So in this new MAC problem, our objective is to estimate an ensemble of augmented vectors. So in each augmented vector, it contains both the input subsurface model and the parameters associated with the machine learning model. And again, the objective is trying to minimize the average value of an ensemble of cost function or objective function. And then in each cost function, again, it contains two terms. Well, the first one is the data mismatch term, and the other one is the regularization term. However, compared to the previous MAC problem, now in this new MAC problem, the data mismatch term has this residue functional present explicitly. And then another subtle difference is that in the regularization term now is a function that depends on both the subsurface model and the parameters of the machine learning model. Then, however, if we compare the structures of this new MAC problem and the previous MAC problem, we can see that actually they share the same mathematical structure. So for this reason, this new MAC problem can still be solved by the IES algorithm. The tiny difference is that now, instead of only estimate the model variables of the subsurface model, we need to jointly estimate both the subsurface model and the parameters associated with the machine learning model. And interestingly, because normally the parameters of a machine learning model do not actually have a clear definition of physical locations, right? So it will be very difficult to apply the conventional physical distance-based localization scheme to tackle the mass effect of small ensemble size locations, right? However, in this case study, we actually apply this integrated workflow that combines both the IES algorithm and the machine learning model to account for the imperfection of a rock physics model from a North Sea field. And then is the field data includes both the seismic data. It's actually a big volume, both the seismic data and the production data. And then into the here is the real field case. We only assimilated the seismic data into this subsurface model, but reserve all the production data for the purpose of performance testing. So then we are going to compare the performance of some algorithms. So here actually what I present is the forecast water production rates from one of the field wells. And then here I have 3 figures. In all these figures, you can see the blue curves. So they represent the forecast production data that are generated by a manually created subsurface model. So this is used as the base case. And then we also see some red dots. Excuse me. So they are the actually the observations in data simulation. And we also see lots of blue curves. So they represent the forecast production data generated by either the initial ensemble of subsurface models or the final ensembles of the subsurface models after data assimilation. So if we compare this, the blue curves in all these 3 figures, then we can see that after data assimilation, these blue curves actually match the red dots better than the blue curves of the initial ensemble. It means that actually data assimilation helps to reduce data mismatch. On the other hand, if you compare the results with respect to the case that no model error correction is conducted, so that's the results in the middle, and a case that model error correction is conducted, so that's corresponding results on the right. Then we can see that at many time instances, with the model error correction, and the quality of forecast data is improved. For instance, if we have a look at this particular time instance, so in the middle, there's no model error correction introduced, model error correction conducted. Then we can see that the forecast, the blue curve says, okay, there's a lot of water at this particular time instance, but the real observation says that actually there's almost no water here. So it's a very wrong forecast. On the other hand, if we introduce model error correction into this data simulation workflow, then we can see that the forecast water actually stays much closer to the real observations. And then we can also check or actually compare the blue curves at other time instances. So in general, I mean, they tend, I mean, with model error correction, the quality of forecast production data will be improved. So then the, Aeneas, how much time do I have?
It's 5 minutes, 5 more minutes.
Oh, 5 minutes. Okay, then I will go through that very quickly. I know that maybe I will have some problem because I spent too much time in the previous topics. So then the last one is about the umbrella IS algorithm. So they have a main objective here is to trying to generalize the IS algorithm to accommodate a larger class of cost functions. And then actually a byproduct of this umbrella algorithm is that we can have a special type of generalized IS algorithm to handle genetic and nonlinear constraints in ensemble data simulation problems. The main idea is that we can incorporate such constraints into the chosen cost function to derive the corresponding IES algorithm. So then let's compare the original, the way that we derived the original conventional IES algorithm and the generalized IES algorithm. So if we want to derive the conventional IES algorithm, as I mentioned before, we solve a MAC problem. And then in the MAC problem, the cost function is in the form of nonlinear least squares, right? And in this generalized IES algorithm, we actually write this cost function in a quite general form. And I can briefly explain the meaning of this new general cost function. So basically, it contains 2 terms again. The first one is the data mismatch term. The second one is the regularization term. Okay, in the data mismatch term, we apply a transform operator gamma to both the observed and the simulated data. And then so for example, you can treat gamma as a discrete wave transform, right, for sparse data representation. So then after transform, this operator D is the distance metric that is used to calculate the difference between the transformed observed data and the transformed simulated data. And similarly, in the regularization term, we have another transform operator phi that maps this updated subsurface model and the background subsurface model into another domain before computing their distances using this operator R. Okay, that's the main idea. Then we can see that this umbrella algorithm written here can approximately solve the previous generalized MAC problem. So then we call this algorithm the generalized AES algorithm. And then we can, if we choose, so here if we choose the cost function in this particular form, right? So here the first term is a data mismatch term. Actually, is the same as the data mismatch term of the original AES algorithm. So it's in the form of nonlinear squares. However, for the regularization term, we let it be a mixture of a different LPQ metric. Okay. The thing is that the values of a P and a Q, they don't have to be equal to each other. They can actually take any positive real number. So because of this, you can imagine that we can have an infinite many possible combination of the values of P and Q. And then for this reason, actually, we can derive infinite many generalized AES algorithms, as long as you change the values P and Q. And then here, W, B, and phi, they are also the quantities that you can also change to derive different types of AES algorithms. So this example serves to explain the richness of the new AES algorithms that we can derive from the generalized cost function. So then to handle the data assimilation problem with soft constraints. So by saying soft constraints, we mean that after data assimilation, the updated model variables might not strictly satisfy the constraints. So it's a soft constraints problem. I mean, let's say it's a task problem for short. So in this task problem, we have three sources of information. One is from the original observation system. The other two is from the equity constraint system and the inequality constraint system, respectively. And then to take into account the presence of these constraints, we can actually choose a particular type of a cost function given in this form. And in this cost function, and the regularization term is in the conventional choice of a quadratic function, right? But of course, you can try different types of regularization term as well. And then for the data mismatch term, it's a mixture of three subterms. So the first term corresponds to the original observation system. And the second and the third term actually take into account these constraint systems. And then this operator D, EQ, and DIN represent some distance metric that measures the constraint system, the distance from the constraint system to the boundary value 0. Okay. So then if we make this particular choice of cost function, we can apply the previously mentioned umbrella algorithm to this particular choice of the cost function to derive a new type of generalized generalized AES algorithm. So I call it a constraint GIS algorithm. So then here I briefly compare the performance of the original AES algorithm and the constraint GIS algorithm in actually very high dimensional 3D case study. And the main point is to show the impact of incorporating the physical constraints. So if we don't incorporate constraints, then we end up with these box plots of Loomis squares at different iteration steps. But after we incorporate these physical constraints, then we can actually make the Loomis squares somewhat lower. Okay, so that means that these algorithms helps to reduce the square error and improve the quality of the estimated subsurface models. So then to conclude, I think I presented a series of technical developments that we have done in the actually past several years in order to address the following noticed issues. So these issues include big data assimilation problem, and then the adverse effects of small ensemble sizes and the effects of model errors, and then the difficulties in incorporating nonlinear constraints into ensemble data assimilation algorithms. Yeah, and then in the future, I mean, I will foresee that there could lots of more developments. Some of them are ongoing, and some of them are in plan. But hopefully, if yeah, you're interested, you can come back to talk to me and to see what I've done. Yeah. Okay, maybe I'm not sure if yeah, if my presentation is really okay to you guys. So if you have any questions, I want to know more details of the methods that I present here, just yeah, feel free to contact me through this email. Yes, so then this leads to the end of my talk. Many thanks.
Okay, no, thank you very much, Xiaolong, for your extraordinary presentation. It was very nice to see how you moved from the fundamentals to the practical part. So it was, for me, also very nice to see the fundamentals. I think it's very important to better understand how things can work in practice. So I think we have a questions from the public, from the audience, actually. We have Randy Steven. He asks, how can we optimally choose the threshold for the correlation-based localization? Is there an interpretability to this threshold, maybe in the physical representation?
Yeah, the threshold value. Okay, the threshold value is yeah, you can in a way. What I did is that you know, if you use the sum correlations as the measure of causality, so in principle, right? If you think of model variable and the data point, if they are uncorrelated, so in principle, there are two correlations should be zero. And then in reality, if you use a finite ensemble size to compute the correlation, then in that case, maybe actually often the sample correlation is not zero. So I just based on this concept, and then I did something actually very quite tricky. If you check this open access paper there, it's quite tricky. We can actually obtain some realizations of the sampling error, right? And then based on these sampling errors, I can estimate the noise levels in the sample correlations. And then based on the estimated noise levels, I use some statistical rules. It's something called the universal rule to calculate a threshold value. So basically, you will say, okay, if the basic idea is to do hypothesis testing, because you are assuming, say, the sample error, the correlation value, the sample correlation error, the sample correlation should be zero. But you found that something is the value is non-zero, then we'll say, oh, okay, is my hypothesis true or not, right? So if you find that the magnitude of the sample correlation is really very far away from zero, then it's very likely that the hypothesis is not correct. This means that okay, there's some true correlations between the model variable and data. But if you cannot reject that hypothesis, it means that the sample correlation is not its magnitude is below the threshold value. Then likely this means that it stays enough close to the mean value, and likely you cannot reject the hypothesis. It means that maybe it's actually its underlying true value is zero, so you cannot reject the hypothesis. And then the implication is that okay, maybe there's actually no correlation between the model variable and data point. So yeah, that's the main idea.
I see. So maybe, I don't know if someone else has a question. Okay, Randy says, thanks, Mr. Wu. Okay.
Yeah, you're very welcome. It's a very good question. If you're interested, just have a look at the paper. I know that because normally we publish in the journals related to petroleum engineering, some of them are not open access, but that one, I mean, yeah, we made it public available. Yeah, so you can check that. Yeah, if you are interested in knowing more details about the other papers, so just contact me. I can send you these papers that's not openly accessible. Yes, because actually we have 3 papers as a series of development. So at the beginning, as I mentioned, I tried this hepside step function and I found that, okay, there's some undesired properties. Then move to this gossiping column function. This becomes smoother. Yeah.
So I don't know if maybe someone else has a question from the audience. Sebastian Joao asks, when removing a data point in the correlation-based localization, is there a way in which we can be certain that that point is not statistically relevant for the correlation matrix?
It's a way the point is not standard relevant. Yeah, I think you can only play that in a statistical sense, because as I mentioned, all these relativities, all is actually relevant is about the hypothesis testing. So the hypothesis itself is that you assume that the true correlation is 0.
Is 0.
Yeah, so if you cannot reject that hypothesis, so it means there's a chance that the true correlation is indeed 0. But you can clearly reject the hypothesis. Then you are proving, oh, okay, there's a true causal relation between the model and one data point. In that case, you should put a higher localization coefficients in the correlation.
Yeah, basically you check statistically that the significance of the correlation, right? So you can
exactly.
It's different from 0 or 3, 0. Yeah, okay.
Yeah, whether it's significantly from away from 0 or is still close enough to 0. So that's the main point there. Then you can develop a lot of stuff.
So there was a question for Sebastian. So I don't know if maybe someone else. I have actually one comment and one question. The first one is with regard to the inflation. You know, the inflation is very important in the context of data assimilation as well. Yeah. Even when we are working with ensemble, I saw a very nice example where you show only in the context of localization, where you show that you avoid the ensemble collapsing by using your strategy, right? Because when you don't use localization, basically the ensemble member collapses to a single point. So we lose a lot of the statistical information in that moment. But the question now is, why don't you use inflation as well? You know that there is a relation between the inflation factor and also the localization step length or radius length. Comments in that direction?
Yeah, exactly. But I think it's a very good point. I mean, a short answer is that while we implicitly consider inflation factor, if let me share my screen again.
Okay, when you use the gamma factor, you inflate.
Yeah, exactly.
I suppose that. Yeah.
You got it. Yeah, exactly. We are going to adapt the gamma value to the iteration process.
It's implicit in this information matrix. We are computing that.
Yeah.
Okay,
exactly.
I remember that. And on the other hand, my question is actually, have you ever maybe thought or tried these precision estimators? Because it seems like it can be potentially exploited in this context, because you actually work on the precision and the estimation of the precision matrix. Well, you estimate the covariance matrix, but then you compute in some sort of free way or free method to solve the implicit linear system. I guess you do that, right? So you're trying maybe just to estimate directly the precision matrix instead of computing the covariance and then not inverting, but solving the linear system?
Okay, maybe I didn't get your question exactly. My point
is that you estimate the covariance matrix, right? And then you log the covariance matrix in the command game. But then in the
we are not estimating the covariance matrix. I'm not sure you mean. I mean the localization matrix.
Yeah. Or you estimate, you make use of the ensemble to the covariances, right?
Yeah.
Now that covariance is rank deficient because you have just a few ensemble members regarding the model dimension.
Yeah, exactly.
You localize the covariance matrix to avoid the impact of spurious correlations.
Yeah, exactly. We actually localize the common game. So it's a bit different. So that's why I say it's a common gain localization.
But when you go to the common gain, you also target the covariances of the variables in the model state.
Yeah, exactly.
My question is whether we can just target like all the you know that the Kalman gain has the power of the covariance metrics of the model state, but also you have the innovation metrics on the observation.
Yeah,
right? My point is that inverse, from my point of view, that inverse can be estimated directly instead of computing the components of the
yeah, I got your point.
And then I think in that way you can just like you have the estimation of your Kalman gain, localized Kalman gain, but also you are localizing the information matrix. So in that way, for me, can improve, for instance, I don't know, maybe
that could be, because I think I didn't try that. I know that you have done lots of this matrix-free stuff. It could be actually something quite interesting. I cannot say anything because I didn't try that idea. So it could be something interesting. I mean, we should definitely look into that. Yeah.
Can be exploited, and then you can get like a sort of localized Kalman gain as well. I think we can talk about that. It would be very important to work on that direction.
Yeah, exactly. Yes. I mean, maybe I need to briefly. I didn't mention the reason why we choose to use Kalman gain. It's the thing is that you know, the Kalman gain is in a dimension of model size by data size. And then our model size, I mean, in the past, the model size is much bigger than the data size.
Yeah.
Because data size maybe suggests several thousand production data. That's the most common data we used. And then for historic reason, you know, and it's more convenient to use the Kalman gain localization because computation is more efficient. Yes.
Yeah, or also just to make use of what you said, to talk about some sort of local domain decomposition as well, just to make
exactly.
On the simulation
process. But I think I have a PhD student who just finished, and he tried this local analysis. So actually, I mentioned that it works very nicely. He also actually combined local analysis with this correlation-based stuff. Because if you do the conventional local analysis, you normally choose the group of data or model values still based on distances, right? Now he replaced the physical distance by localization, and that works quite well.
All right. Yeah. So my last question, so because we are on the time, but I have a question as well. So you talk about combining information from the numerical simulations and also having a machine learning model, right? And then you tune the parameters of the machine learning model with regard to the information coming from the simulation as well, and the observations. So my question is, how do you localize? How do you relate? You can speak briefly in that direction. How do you correlate the model variables to the parameters of the model of the machine learning method?
Because you can actually, if you add that, if you add the residue functional into an existing, say, numerical simulator, then in fact, it's like the effective forward simulator actually takes both the model variable and the machine learning model parameter as the input, right?
It's just like an augmented state.
Yeah, augmented. Yeah. So that's why I said the structure. The structure is the same. You don't have to do anything. Yeah, don't have to do anything extra. So that's why that's the beauty of this augmented stuff.
Yeah, that's it. Yeah, and then you can get all the information from whatever you estimate.
Yeah, you can look.
Yeah,
that's no problem.
Okay, makes sense. Makes complete sense. Excellent. That's actually the point. I have used like augmented state, but to compute parameters from the model. You know that we perturbate the parameters, and then we run the model with these parameters, and then we get some insights about how variables and all the parameters. But I have never tried making use, for instance, of a machine learning model. I mean, it should work similar, right?
Yeah, I think so. Yeah, it's quite mathematically, it's straightforward. Yeah.
Okay, excellent. Okay, thank you very much again for your further presentation.
Thank you, everyone. Yes, and I wish you a very nice weekend. I should definitely. Maybe I should take the chance to mention that next year we are going to organize a physical Yankee workshop. If by chance you can attend, you are really more than welcome. Yes.
Okay.
And then let's keep in contact. Yeah.
Of course. We will be there. We will be there. I'm sure that Javier will help me to get some funds to to go to the workshop.
And good luck. Yes, good luck to the proposal. Yes.
Okay. Okay.
Yes.
David says that thanks. It has been an excellent presentation. David is also a faculty member from the department. I'm pretty sure Sebastián David Ariza, Sebastián David Ariza is a student. Rolando Beltran was he formed as a PhD here in Norte. Sebastián was a master's student. Now he's an instructor in numerical methods. Basically, Felipe is a master's student as well. And Miguel is the coordinator of the PhD program here in Norte in systems engineering. So it's like this is like a local. Okay.
Hello.
Thank you very much. Have
thank you.
weekend.
Thank you for
your very nice presentation.
Okay. I'll talk to you later.
Weekend.
Bye bye.
Bye bye.